Well, in this lecture, I'm going to be talking about few-shot learning, but we use a protonet, but a kind of protonet that when we want to calculate the distances, we use the hypersphere, Euclidean norm, and the hypersphere. It means the distance to the surface of the hypersphere. But still, it is few-shot classification, but the way that we do it in the protonet is the way we calculate the distances is a little bit different. So I'm going to be focusing on this important paper in 2022 from the best university of China and the Alibaba Group. So in few-shot classification, key points to make the learning phase effective are to construct expressive class-level representations and design appropriate metrics. However, previous studies often struggle to reconcile the expressivity of representations and the conciseness of the metrics. When modeling class-level information, vanilla embeddings can make classification difficult due to lack of capacity, whereas complex statistical modeling hinders metric interpretation. To address the issue simultaneously, this paper presents a simple and effective approach from the geometrical perspective, dubbed as hypersphere prototypes. Specifically, our method represents class information as hypersphere. So different classes, different hypersphere, you see, is like this. So it's much better, you can create much larger amount of classes because you don't have to just be 100 representation, and it's more suitable for analysis as well, as you will see. So with the learnable, so these are the advantages. With the learnable parameters, unique class representations can be easily constructed and learned without additional restrictions. Using areas instead of points as class representations, the expressive capability will be greatly enhanced. So increasing the reliability of few-shot classification. The metric design is intuitive for hypersphere representation, which is the distance from a data point to the surface of the hypersphere. Remember, we are calculating distance to the surface only. And as a fundamental method of few-shot classification, our method demonstrates remarkable effectiveness, generality, and compatibility with other technologies. But let me repeat this one. So instead of points that say these points represent this protonet, I would say that an area represents a class. So we consider the episodic N-way K-shot few-shot classification paradigm. Given a large-scale annotated training data, our goal is to learn a model that makes accurate predictions for a set of new classes, containing only a few labeled examples for training. So we have support and queries, same as usual, but now instead of calculating distance like Euclidean, we still do Euclidean, but it is embedded, the points are embedded in a hypersphere. So that is why it is called hyperproto. Instead of protonet, the original article, we call it hyperproto. So if we have a point, we have center and radius. So different classes, we have different hyperspheres that represent different classes. For example, another class could be here. Another class could be here. And so the central idea is to learn a hypersphere. How do we learn it? You just learn the radius and the center and the radius. And then, so as I said, Sn is just a set of sampled instances of the nth class. So for each class, we have a different hypersphere, but the rest of that is standard because we are calculating this softmax over the matrix. And the parameters of F and hypersphere are optimized based on cross entropy. We always do it using cross entropy. And so this is the loss because everything is standard, but how we calculate the distance is now different. So although the centers and radii are stored and optimized continuously in training, the whole process is still episodic, as in each episode the samples in the query set are only evaluated against the classes in that single episode instead of the global training class set. So a standard episodic evaluation is adopted to handle unseen classes, where we estimate prototype centers and the radius in closed form. In the episodic evaluation procedure, hyperproto directly takes the mean of instance embeddings as the centers and the mean distance of each instance to the center as the radius. So they are using it for name entity recognition, relation extraction. For example, they use this dataset, few-nerd intra and few-nerd inter. Both of them, so we expect for the one shot to have a lower accuracy, and it is lower, by the way. This one is lower than 5 shot, which is 68. 61 is lower than 67. 48 should be lower than 60, and it is. 41 should be less than 53, and it is. And also, we want to use for relation extraction, few-shot learning for relation extraction. The same way, we expect 5-way, for example, to be less accurate than 10-way because it's harder. One-shot to be, we expect the one-shot to be harder than 5-shot. And as you see, 64 is less than 80. 66 is less than 80, so all of these are less than the 5-way, but the 5 shots, because 5 shot it means 5 examples. You have more examples to train, so the chance that you can, I don't say overfit, but you find the true nature of the data is stronger. And for few relative, they also use the domain adaptation, the data set. In transfer learning, when we go from one domain to another domain, test another domain, we have a domain shift problem. That's why there are some techniques in deep learning. We use domain adaptation to handle this problem. But it's so strange, very few people consider the importance of this domain adaptation. And also we can do generalization of our method. So we have introduced the mechanism of hypersphere prototypes in Euclidean space, but we can generalize the cone-like hyperproto. You see, it's like cone. And there are different methods that we can generalize. For example, Gaussian proto. Of course, from the probability perspective, each class can be characterized by a distribution in a multidimensional feature space. The measurement of a query sample to the nth class can thus be represented by the negative likelihood. So we can simply assume that each class is subject to a Gaussian distribution. And to reduce the number of parameters and better guarantee the positive semi-definite feature, we can further restrict the covariance matrix to be a diagonal matrix. So it is diagonal, so your covariance is a diagonal matrix, and then you can calculate everything explicitly.